Thanks, John. Greetings. Today's topic is accepting special waste and maintaining stability. This is a newspaper cartoon from a landfill failure near Cincinnati. And what we don't want to happen is shift happening, as the cartoon says. There are a lot of reasons that shift happens, and today's reason is special waste. The outline of the presentation is shown here, 2, 4, 5 main topics, and then a real brief summary. So the first is a case history. And this is a case history involving the disposal of special waste. In this particular case, it involved 7.5 million cubic yards of a sludge material, project valued at about $500 million, 450 million, 10-year project. And the issue was separating low strength waste, LSW, and direct disposal waste. That's a very key issue because direct disposal waste can be placed in with the traditional MSW, if it's an MSW facility. For example, this one is an MSW facility. If it's a low strength waste or an LSW, it must be handled in a separate way. And generally, the cost of an LSW is more than DDW, or direct disposal. In this particular case, the difference was $20 per ton. There were initial estimates of 500,000 tons. So at the beginning of the project, the difference was about $10 million. It increased because the volume of LSW increased, in part due to some of the problems with the specification, which I'll talk about in just a minute. So this classification is important, usually has a significant amount of money associated with it. Here's the processing facility where the initially high moisture content sludge was processed to try to reduce it, solidify it, but it still had a fairly low strength, as you'll see in just a minute. That material was then placed in an MSW landfill, and shortly thereafter, cracks and bulging started appearing in the slopes of the facility. The initial plan was to have slopes of 3 horizontal to 1 vertical. There were no requirements of a slope setback, which I'll talk about in just a minute, and that is the distance from the slope face back to the LSW, or low strength waste. In this particular situation, the slopes had to be flattened and berms created for stability. Most of the area was flattened to about 4 horizontal to 1 vertical. So one of the big questions, if shift does happen, is how deep is the shift? In these particular photographs, you can see in this area the shift was fairly shallow, generally less than about 10 feet. And the toe is shown on this slide here where my laser pointer is. So it was concluded that this slope movement did not affect the bottom liner system. However, depending on the depth of the movement and the depth at which the LSW is placed, it could impact the bottom liner system. And of course, that brings in a whole nother set of issues to deal with. But at this particular site, it was determined that the depth of movement was above the bottom liner system. So before accepting low strength waste or special waste, a waste acceptance and operation plan should be developed and agreed upon through all the parties. And that plan should include strength requirements for the low strength waste, an evaluation of the interim and final slopes, and I have interim in red. A lot of the case histories involving waste containment facilities point to the interim slopes being the critical condition, not the final slope. So don't forget to evaluate and have a plan for evaluating the interim slopes. Then the big question becomes the testing program. After you select the strength, requirements. How do you test it? How often do you test it? And the testing has to be fairly quick so the material can be deposited fairly quickly and not slow up the process. In this particular case, the slope was reduced to about 4 horizontal to 1. The other thing that items that should be included in the waste acceptance plan are the maximum fill height and whether slope benches should be included in the facility. So let's turn to the shear strength specification. This is where some geotechnical engineering comes into our geosynthetics presentations. And so this is the contract specification that was in operation for selecting the low strength waste, and actually the DW, or the direct deposit waste. So the DW only had to meet one of the following 4 criteria, A, B, C, or D. Only one of the criteria. So notice there's an or at after each one. So first is minimum unconfined compressive strength of 0.8 tons per square foot, or minimum cohesive strength, and we're going to talk about what cohesive strength means in a minute, 800 pounds per square foot, or PSF. C, a minimum short-term friction angle of 25 degrees, or finally, define combinations of cohesive and short-term frictional strength that provide a factor of safety for the landfill slopes as determined through slope stability modeling, at least equivalent to B or C. So D allows the engineer to look at different combinations of this cohesive strength and short-term friction angle, which could be an apple and a pineapple, actually, as you'll see in a minute, to somehow come up with a factor of safety that's at least equivalent to what you would get with B or C. Well, the problem with that criteria right out of the gate is most of you know that you can calculate a factor of safety using a variety of input parameters and essentially calculate whatever factor of safety you want. So this is a very vague criterion, letter D. So if this is going to be the way you specify the low strength waste, you should put a factor of safety into this criterion and be specific about the stability analyses. So with that, let me focus in on A, B, and C. Okay, so A is a minimum unconfined compressive strength, so that's running an unconfined compression test, which is good. It's fairly quick, and so that could work with the processing of the material and then transporting it and disposing of it. However, you have to create a right circular cylinder to run this test. So I'm going to suggest some other tests in just a minute, but this isn't bad. An unconfined compressive strength, if you're familiar with concrete cylinders, this is very similar to a concrete cylinder test, compression test, but on a right circular cylinder of the processed sludge. B and C are really kind of confusing. So B says minimum cohesive strength, which you would have to assume is the undrained shear strength of 800 pounds per square foot. So that means you would have to run a triaxial compression test or take the unconfined compressive strength and divide by 2 to get the undrained shear strength. Or conduct a unconsolidated undrained triaxial compression test, which is even harder. So this is a difficult criterion, B. C is even more kind of confusing because it says a short-term frictional strength. So in general, frictional strengths develop under drained conditions, not short-term undrained conditions. In addition, you'll see in a slide in a minute that if the sludge is truly saturated, the friction angle in an undrained condition will be 0, not 25 degrees. So 25 degrees really corresponds to an unsaturated material, if it truly is unsaturated. So you can see there's some confusion in the shear strength criteria selected for inclusion in the specification. I think having a specific shear strength specification is the way to go, but it has to be geotechnically sound and very readily testable versus D, which is a fairly vague spec. Okay, with that, let me talk a little bit about geotechnical and soil mechanics here. If you have a saturated fine-grained material such as a sludge and it's saturated, you would get a phi equals 0 condition, as you see in this top graph, and the vertical intercept on the left is the undrained shear strength, which I think is the minimum cohesive strength that's listed in criterion B as in boy. If it's unsaturated or partially saturated, you can see the envelope will dip down towards the origin because as you apply confining pressure, there is a change in void ratio and an increase in strength. So the 25 degrees that applies to criterion C as in Charlie could work in this portion, the initial part of the envelope, a friction angle of 25 degrees. So that might work if it's truly partially saturated or unsaturated. So back to the shear strength specification. If the sludge is saturated, phi is equal to 0, not 25, so that voids criterion C. And criterion B, then the intercept would be the undrained shear strength, and that's 1/2 of the unconfined compressive strength, which is basically 1/2 of criterion A. So criterion A is a minimum unconfined compressive strength of 0.8 tons per square foot, which is 1600 PSF. So if I take half of A, boom, I get 800 pounds per square foot. So indirectly, A and B are equal to each other if the sludge remains saturated. Now, I think you can see the confusion that developed and could develop with this specification. First, the different units make it really confusing to the people interpreting it to understand what strengths are what. So A could have just said minimum unconfined compressive strength of 1600 PSF. So then you could readily see that 1600 is half or twice what 800 PSF. So you would see that these two are related if the material is saturated. So that's the spec. And as I mentioned, 0.8 is 1600. And if you go to Peck, Hansen, and Thornburg's Foundation Engineering book to try to put that number into proper context, that would be a soil that has a medium consistency, penetrated several inches by your thumb with moderate effort. So even if the waste was classified as direct deposit waste, DDW, it's still pretty weak. So slope stability still could be a concern if you followed the criterion A or B. Clearly the LSW is even weaker, and so you can see why slope stability problems did develop, and it shouldn't have been that big of a surprise. And that's where the slope setback comes in that I'll talk about in just a minute. So with that, that's a review of the specs. Here's some of the data of the processed sludge that was tested, and the dashed red line right across the slide here is an undrained shear strength or a cohesive strength, according to the specification, of 800 pounds per square foot. So notice there's a lot above the dashed red line, which got DDW, so no additional $20 per ton assessed, but you can see there are a number of points below 800 PSF, and these were all those loads and days of production were assessed a much higher $20 per ton disposal rate. So this is graph based on degree of saturation. Notice that the majority of this data is less than a degree of saturation of 100%. There are 3 points over here at 100% where that would make the sludge saturated, and you would have a phi equals 0 condition, and the intercept would be the undrained shear strength, those 3 points. The rest of the data is all unsaturated, and that points to using the third criterion, C, where it said a minimum short-term friction angle of 25 degrees. So that's the importance of separating and developing criteria that matches the consistency, degree of saturation of your special waste. Here's that same data based on moisture content. You can see some of the moisture contents as high as 120%. The majority in around 80 to 90% in the middle of the graph. And so a number of the points falling below 800 pounds per square foot of undrained shear strength. So all the points below this dashed red line would be accepted at the higher disposal rate of an additional $20 per ton. Okay, so back to the spec. A, B, C, or D. A and B are only viable if the material is going to be saturated, and if it's saturated, there's no difference between A and B, so it's really kind of confusing to have both of those. You could have just had one. C, if the material is unsaturated, this is probably a reasonable specification, but you would write it as minimum drain friction angle instead of short term. Short term indicates an undrained condition, so that's really confusing. If it was really short term and undrained, this friction angle would be 0 if the material was saturated. And D, as in David, is not appropriate unless additional guideline is going to be presented in D, such as a factor of safety for the slopes given these different strength parameters. So D is not recommended. Okay, so I think a quantitative specification should be used for special waste. Again, I mentioned if you think it's going to be saturated, you could use an unconfined compressive strength. If you think it's going to be partially saturated, you could use a friction angle and call it a drain friction angle, in this particular case, 25 degrees. What shouldn't be used as a qualitative specification. This has led to significant problems. For example, these terms have been used to describe the special waste before placement, and it's led to, first of all, problems interpreting what it means, and also slope problems. First, support its own weight. Walk on it. Support material placed over it. Well, how much is going to be placed over it? Capable of being worked by low ground pressure equipment. A specification that says just ensure stable slopes. Maintain slope stability. One had factor of safety greater than 1.5. Now that's very specific. That's good. That could be applied in spec D that we just talked about and used for slope stability analyses. Construct stable 3 horizontal to 1 vertical slopes. Maybe. Medium consistency. Well, that's very vague. I showed you Peck, Hansen, and Thornburn's description of medium consistency. Very hard to inspect and enforce that criteria. So back to the top, a quantitative specification for the special waste is recommended. Okay, so other tests that can be done quicker than these laboratory tests of triaxial compression and unconfined compression. You could set it up as a pocket penetrometer in the upper left graph, a vane shear device in the field or in the laboratory. The lower left is a field vane in a soft clay with a torque wrench, and that's calibrated to undrained shear strength. Or the laboratory vane, where I'm pointing to the small vane in the lab vane. That's turned in the sludge material, and it gives you an undrained shear strength that could be used in the specification. or another field device similar to the pocket penetrometer on the upper left is a torr vane device where the vanes are pushed into the special waste, turned, and this dial on the top is related to the undrained shear strength. So these are much quicker tests, can perform quicker than triaxial and unconfined compression, and that could facilitate inspecting the materials before deposition. That brings me to the next big problem is how often do you test it and how do you test it? So this is a table from various projects that I've assembled. If you use unconfined compressive strength, that's ASTM D2166, you would have an acceptance limit of 0.8 if you use the criterion A that I talked about. That could be done in the lab. Primarily field would be the pocket penetrometer or the torr vane I just showed you. Test frequency once every 1,000 cubic yards. After the first 10,000 cubic yards, maybe once every 5,000 cubic yards. Undrained shear strength measured with the vane shear, whether it's in the field, ASTM D2573, or in the lab, which is 4648, and you would use similar testing frequency. Now, if you went to more sophisticated triaxial compression tests and measured undrained shear strength, the unconsolidated undrained triaxial test is D2850, and the consolidated undrained test with pore pressure measurements is D4767. You could have similar strength criteria as reported above. This would be done only in the lab, and this is a much more difficult test, so you would run it maybe once in the first 10,000 yards, and then maybe once in every 30,000 cubic yards. So this is a difficult test, maybe not one that you want to use as the specification check. Finally, effective stress shear strength parameters if you think the material will be unsaturated. So you could use the consolidated undrained test with pore pressure measurements, again, very difficult to perform, or run direct shear tests, which is D3080, and make sure the friction angle is greater than or equal to 25 degrees. So those are some recommendations for testing and test frequency. Okay, placement specification. Where do we place this material? And this comes into the waste acceptance plan and the operating procedure. First, and this is not a joke, make sure it ends up in the correct landfill cell. If that waste is supposed to go in a certain cell for stability reasons or operational reasons, make sure that's clearly laid out. It doesn't always end up in the right landfill cell, unfortunately. And in the field, shift does happen and things do happen. So make sure that the waste is designated for the appropriate landfill cell. Next is the slope setback. I'm going to spend several slides talking about the slope setback and how to incorporate that in stability analyses. But in general, the farther back the waste can be placed from the slope, the greater stability and the less opportunity for leachate outbreaks. Another criterion in the placement specification is allowing time for the low strength waste to dry out and increase strength a little bit. This is difficult because additional loads come in, they have to be placed, but the working face or cell could be organized such that there is some time allowed to dry out portions of the special waste. Compact and thin lifts, generally less than 12 inches, and the thinner the lift, the quicker it dries out. I'll talk a little bit about mixing with the MSW. That's helpful because you break up the sludge and very good in terms of shear strength, but it's hard to do in practice to get it worked into the MSW. I'll show you a slide in just a minute that shows you need about 40%. Once the special waste hits 40% of the mass, it starts behaving more like the low strength waste instead of the MSW. Promote runoff, so there's no ponding to increase infiltration. Generally, with special waste, the slope inclination that seems to be working is about 4 horizontal to 1 horizontal. That's flat, certainly flatter than 3 horizontal to 1 vertical, but it seems to be working, especially if the slope setback of 100 feet is not going to be met. Okay, I mentioned the percentage of waste. This is a slide from Dr. Rudy Bonaparte's Terzaghi lecture given in 2018. It's a great figure, but the even better news is Dr. Bonaparte has agreed to give our January 2020 webinar, and in that webinar he will present his excellent Terzaghi lecture and give you even more detail about this figure. So please plan on joining us for Rudy Bonaparte's January 2020 webinar, which will be his Terzaghi lecture, Stability of Waste Containment Facilities. So this is a graph from Rudy's Terzaghi lecture, and it shows there's a big drop in strength. This light blue line, that's 40% low strength waste, and the next darker blue line that I'm pointing to is 50% low strength waste. So you can see there's a big drop in shear resistance when the low strength waste exceeds about 40%. And Rudy will give you additional details on his plot here, but a round number is 40%. And so test results show MSW / low strength waste mixtures become weaker when the percentage of low strength waste is 40% or greater. At higher percentages, say 70 or 80, way down here, the MSW / LSW mixture essentially behaves like the sludge. Okay, so next is the slope setback. And this is a good thing to do, but it reduces the available space in that particular landfill cell. And I'll show you that with some stability analyses in just a minute. It can create a low hydraulic conductivity zone where liquid or gas pressure, which I'll demonstrate in just a minute, can build up above and or below this layer. So I'll show you an example of calculating excess pore pressure and gas pressure around this low strength waste. Okay, slope stability analyses. So in general, MSW is strong material. That's been the really good news of the slope stability issues related to waste containment facilities. In 2000, we presented some recommendations for the shear strength of fresh municipal solid waste, as you see on the left. Fairly strong interconnected material, sort of like a reinforced mass. And you could use a friction angle of 35 degrees and a cohesion intercept of 25 kPa, or about 500 PSF. And that stood until about 2008, where we modified that to have a stress-dependent strength envelope for fresh MSW, which is shown in these two graphs. And that can be boiled down to these two strength parameter combinations. For stresses less than 200 kPa, you have a friction angle of 35 and 6, cohesion of 6. Greater than 200, a friction angle flattens off to 30, and the cohesion intercept is 30 kPa. So if you're running stability analyses with a computer program, you can input this envelope into your slope stability analysis using the shear stress, normal stress and shear stress table off here on the right. So the envelope passes through the origin, 0, 0. At 200 kPa, the shear stress is 146, and that corresponds to 35 degrees and 6 kPa. And then at 500, say for example, the low stress graph right here, your strength envelope would correspond to 319 kPa to show the stress dependent nature of it. So if you're going to go past 500 kPa, which is about 10,000 pounds per square foot, you can extend this table like in this high stress graph over here out to even higher kPa, and you'll have the stress-dependent strength envelope for the MSW. So use a stress-dependent strength envelope for the MSW as well as the bottom liner system geosynthetics. Okay, so that was fresh MSW. If you have leachate recirculation, you should reduce that to just a friction angle of 32 degrees. And if your facility experiences elevated temperatures and undergoes thermal degradation, you should lower the friction angle even further to about 20 degrees. And that's the red line and the dark blue line for recirculation superimposed on the graph that I showed you on the prior slide. Okay, so let's talk about stability analyses. Here is my typical cross section. The bottom liner system is on the bottom and up the side slope. I have a liquid level in the leachate collection and removal system of only a foot to comply with regulations. And then I have a low strength zone or layer that gets put into the facility, and that's this shaded brown area. So in your stability analysis, you can model this weak zone or low strength zone with a different material type. And then you should investigate non-circular failure surfaces, not circular failure surfaces. Circular failure surfaces are only applicable to homogeneous materials. And this is clearly not a homogeneous material, and clearly MSW is not homogeneous. So the non-circular failure surface would pass from the surface down to the weak layer and out the toe of the slope. And if you remember the photographs from the beginning, you saw a very shallow non-circular failure surface occurring with that low strength waste. The surface was less than 10 feet deep, so it went from the crest down and then it bulged out at the toe of the slope like that. Okay, so this is the easy example. Now, this has no slope setback, so notice the LSW is really close to the slope face. And so now you can see that you only pick up a little bit of strength between the end of the low strength waste and the slope face. Okay, you get some strength along the back portion of the non-circular failure surface, but it's limited because the normal stress acting on this part of the failure surface is essentially 1/2 of what it is acting on the horizontal portion. So we generally get a significantly less strength mobilized on the back scarp of our non-circular failure surface. So what you really want to do is maximize the length of this horizontal or near horizontal portion that is not in the LSW. And that's the whole idea behind the slope setback, which is shown here. So if I use a slope setback of 100 feet, that pushes the LSW back 100 feet. Now I have a significant length of my failure surface from the LSW through strong, fresh MSW, which increases my stability and factor of safety. Now, we can actually have a big zone of LSW, which I just added to this diagram. So you can see, having it further back, I only pick up still a small part of the bigger zone of LSW, and my factor of safety shouldn't change that much. But if I move this big block of low strength waste closer to the slope face, you'll see that the factor of safety will decrease pretty quickly. Okay, so let's talk about leachate and gas pressure, as I mentioned before. The upper equation that I'm presenting and circling with my laser pointer is the factor of safety due to moment equilibrium, and it's the cohesion plus the normal stress times tangent of the friction angle divided by the weight of the slide mass times the sine of the slope angle, and that's multiplied by the length of the failure surface. So the interesting piece is the effective stress, sigma prime. And so part of that is the pore pressure or gas pressure that's highlighted in the red box, and that gets subtracted from the total stress. So if I have a pore pressure that exceeds the total stress, I basically have a liquid or a liquefaction condition. The total stress is just the gamma of the municipal solid waste, for example, times the height of the waste. The pore pressure is the liquid level or height of leachate times the unit weight of water, generally 62.4 pounds per cubic foot. So that's the liquid pressure. Now we can also use the pore pressure term to include gas pressure. So gas pressure is the unit weight of gas times the pressure head of the gas, which I'll show you in just a minute. So I can take the gas pressure that might develop under the LSW or on top of the LSW into my slope stability calculation. And so as my gas pressure increases, my effective stress decreases and my factor of safety would decrease as well. So how do we do this in the stability analysis? So leachate level first. So we can apply an additional liquid level, say a perched level on top of our LSW zone. So this is the same cross section I showed you earlier with no setback. The sludge or fine grain waste builds up liquid on top of it, and now I can have a perched liquid level on top of the LSW, which reduces the effective stress along the horizontal portion of this non-circular failure surface. So you can include that in your slope stability analyses with a second piezometric level in the analysis. The first piezometric level is the 1 foot of head in the leachate collection and removal system, or if you don't want to include that or you don't think it has a big effect on stability, you could just have a single level and have it perched on top of the low strength waste. We could have multiple levels of low strength waste. How about that? We have 2 layers of low strength waste, and now we could have 3 levels, 2 perched and the leachate collection and removal, or just the 2 perched levels. And now you would look at non-circular failure surfaces through both layers of low strength waste, including the level of perched liquid. And you can vary the level of the perched liquid, certainly on the bottom one. As time goes on, generally this level will increase a little bit, and that reduces the factor of safety. Notice though, the deeper surface has a larger setback from the slope, so maybe that increase in perched liquid does not have to or cause slope stability problems. Now the last bullet here is as-built conditions. So in the design process, you might assume that there are 2 levels of low strength waste, but shift happens in the field and maybe you have 3 or 4 levels of low strength waste. So you should always update your stability analyses to reflect the as-built conditions. So if the processing is producing more low strength waste than you thought, rerun the slope stability analysis with maybe a bigger zone or a thicker zone of LSW, or maybe more zones of LSW, just to make sure you're tracking the stability as the facility's filling up. Gas pressure. So that those prior slides were liquid or leachate pressure. Here's gas pressure could build up on the bottom of the sludge layer or fine grain layer, and now we could have a non-circular surface go through the LSW along the bottom of it and out the slope to the slope face due to the high gas pressures acting underneath the LSW. We can incorporate those in the stability analyses using piezometric or a pore pressure, and we can calculate the gas pressure using this expression. Gas pressure is the unit weight of gas times the pressure head of gas. Rick Teal proposed a gas unit weight of 12.8 newtons per cubic meter in 1998. And then you take the pressure head from the gas. So the graph on the right is pressure head from various gas extraction wells in the area where the low strength waste is going to be placed or adjacent to it. And you can use these pressure heads now to calculate what your gas pressure will be, because if this is close to the area that will be receiving the special waste, the air conductivity of the waste can transmit these pressure heads over to your area where low special waste is. And so this would be a reasonable estimate of the gas pressure to apply in your stability analysis. So notice the pressure head at this particular site ranges from about 2 or 3 feet to almost 70 feet at the top here. So I'm going to use those numbers, those gas pressure heads and the gas unit weight in just a minute in an example. So here's the example. It's a 3-to-1 slope. Slip surfaces are going to pass through the waste. This big piece of material right here is the perimeter berm, stabilizing the slope. The bottom liner system goes up the perimeter berm, and there's an anchor trench at the top right here. And so we're going to look at failure surfaces that come through the waste, hit the perimeter berm, and come up. The berm strength is friction angle of 30 and a cohesion of 0, and I'm going to vary the leachate levels and gas pressures in the waste to show you how dramatic the factor of safety change can be. So here is the initial level, very low. Look, we get a factor of safety of over 3. If I use the stress-dependent strength envelope for MSW, you can see it drops the factor of safety from 3.3 to 2.75, so a pretty big effect on the calculated factor of safety using a stress-dependent envelope for the MSW, as I suggested before. This number here should be 0.35 instead of 0.25. Okay, now let's put the high leachate level in. Look, the factors of safety drop from 1.5 to less than 1, and I add a gas pressure from 3 to 70 feet, and that'll reduce the factor of safety even further, as you see in this table. So if I use non-degraded waste, thermally degraded waste, and a low liquid level, I get 3.3 to 2.7. If I use a liquid level at 364, which is this upper liquid level right there, and a gas pressure corresponding to 270, which is 70 feet of pressure head, I get 1.5 to less than 1. And then if I use thermally degraded waste strength and the gas liquid level in the gas wells and a gas pressure, you can see I can get a factor of safety less than 1. So gas pressure and leachate pressure do decrease the factor of safety pretty quickly, and that's why your stability analyses with low strength waste should reflect liquid and gas pressure. Also, use stress dependent strength envelopes to model the MSW, the sludge if it's available, and also the bottom liner system, geosynthetics. Okay, I'm close, quarter of. Maybe I can run through slope monitoring really quick. This is a case history, I've discussed it previously, that shows just a small amount of cracking on the slope. You can see it's about 1/4 of an inch. It grew to maybe 1 inch to 1.5 inches. Results in significant movement in the bottom liner system. That's the crest of the slope. Again, about 1 inch of movement. And that resulted in about 10 feet of geomembrane being collected at the toe of the slope. Based on that, it was decided to excavate the waste. The tear in the geomembrane was found. Those wrinkles were not present at the toe of the slope, which was ran right here in front of this collection trench. The movement occurred at the bottom of the geomembrane with an unreinforced bentonite GCL, and also some movement on the top of the geomembrane between the geonet and the geomembrane. Failure surface goes from the crest down to the liner system, out the toe. About 10 feet of geomembrane wrinkled up at the toe and only about an inch of cracking at the top of the slope. So MSW is not a rigid block. So if there are cracks developed in the slope, that means there could be significant movement within the waist. The case history I showed you, we determined that the depth of movement was only about 10 feet, so we weren't concerned about the liner system. But in other cases, it could mean that there is some movement along the bottom liner system. Okay, monitor these tension cracks, put telltales across them so you can estimate the magnitude of movement and the rate of movement. So to wrap up, and hopefully there'll be some questions, the majority of landfills are constructed and operated safely. Special wastes present a unique challenge to us in this facility, but they can be designed and operated safely without a problem using state-of-the practice, not state-of-the-art stability analyses and techniques. Increased leachate and gas pressure around these low-strength wastes can decrease stability, as well as the lower shear strength values that you use for the low-strength waste. These are the papers that are referenced in my slides. These will be posted on the website, the FGI website, in PDFs. Every paper that was referenced is listed here, and there will be a PDF along with the video and my slides on the FGI website. Here's our contact information. We're trying to schedule the November webinar on leak location surveys. We'll keep you posted on that. But in December, I will team up with the Australian chapter of the International Geosynthetic Society and give a webinar on factory fabrication, installation, and testing of geomembranes. It's being offered in Sydney, Australia at noon the day before, so that would be December 9th. So if you want to attend it live, it will be Tuesday at 9 p.m. December 10th. We'll also have it as recorded and on our website. The FGI website is available, a lot of important information, latest specifications, guidelines, technical papers, installation details are available on the website. So with that, John, I hope there's some questions.
Yes, Tim, thank you so much. We've gotten a couple of questions. First is related to the paint filter test. So many projects I see where sludges are coming into the landfill, we rely so heavily on the paint filter, and we don't progress beyond the paint filter into unconfined or UU, let alone getting into CU, where you would need a real homogeneous, consistent waste stream coming into your fill. Can you speak to that a little bit?
Yeah, so John, that's a great question. I obviously left out the filter, the paint filter test, because you really don't get something out of that you can use directly in a slope stability analysis. That's what we're really trying to do, is to ensure slope stability. So that's why I focus more on these geotechnical tests. If you're going to evaluate stability, unless you can develop a correlation between the paint filter test and like an unconfined compressive strength.
Okay, so we're locked into paint filter from a regulatory requirement. I just don't ever, I've personally never seen us move beyond paint filter into things more advanced to ensure our stability. And maybe that's a industry problem that we need to change to make sure that our waste bodies are stable.
Right.
Next question is, in landslide case histories, we are familiar with lines of survey stakes are often used to monitor. What do you think about this practice?
Yes, the survey stake lines have also been used in landfills. There could be just metal survey points or hubs installed in a slope, and they're monitored regularly. that has been done for a couple of these elevated temperature case histories, and that's been helpful because we're able to plot the movement of those hubs, and we can see how the slope is sort of bulging out and then coming back in. So that's probably the preferred way to monitor the slope, because we really can't install an inclinometer in a facility that has a bottom liner system. We can't punch the inclinometer through the bottom liner system. We can stop the inclinometer in the waste, and it can move a little bit. It gives us an indication of how much it's moving. And of course, monitoring the movement of the gas wells as well. So any of those methods are viable.
All right, thank you. Next question. How much effort has been put into the concept that when low strength material makes up 40% or more of the overall embankment material, it controls the strength modeling? Looking forward to the Bonaparte 2020 continuing this discussion. So maybe we get Rudy to revisit at the start of his.
Yeah, that came out of a case history in Pennsylvania, and there are other people measuring the strength of different mixtures of waste and low strength material or sludge. Some of it's going on at LSU with Naveed Jafari as well. So that's a very active area of research. But right now, 40% is the number.
All right. When a material is not completely homogeneous, such as tailings, how do you decide whether you have a circular failure or an edge type failure analysis? Which one's the preferred analysis?
Okay. If the material is homogeneous and isotropic, okay, what do those two words mean? Homogeneous means it's the same in all direction. Isotropic means it has the same engineering properties in all directions. It's only in those materials that we develop circular failure surfaces. This has come out of soil mechanics and geotechnical engineering for soft clays, which are generally homogeneous and isotropic. What's happened is the stability analysis is very easy with a circle. So all computer programs, you can do it by hand, use circles. But it is rarely the case where you have a circular failure surface, especially in waste containment facilities.
All right. Next question. One of the viewers has a landslide failure where they saw wrinkles in the geomembrane resembling ripples in a pond on the flanks of the side of the rotation. Did you happen to see this phenomena in your case study?
Okay, great question. So this was developed, and I've only put in a couple slides on this. If you look closely in the foreground, there's a leachate collection trench right running across the bottom of this photograph right there. So there was a pipe in there. This cell that's being constructed filled up. The toe was roughly about at this collection trench. And to bring the next cell online, which is to the right, the toe of the slope was excavated to put a cap over top of this leachate collection trench. So leachate then would flow from this cell into the adjacent cell and be collected at the main sump. So that was the only reason that the toe was excavated, and that's when all of these wrinkles were found. And if you lifted up those wrinkles, there'd be about 10 feet of material wadded up there. So the question, the person asking the question should go and look at as-built photographs like this one, and that's why we went and found it. If there was not significant wrinkles when it was constructed, as you see here, adjacent to this leachate collection trench, those wrinkles occurred after construction and have to be due to slope movement. And that led eventually to the excavation of this waste after some very lively discussion.
Sounds like our viewer might have a problem. All right, we've got one more question here. If you toggle to the slide of the factor to safety between the 2000 paper and the 2000, is there a good clearinghouse of like what's right and wrong? Like clearly, if you went with the 2000 methodology, you could get yourself into trouble. You go back and reevaluate with the 2008 methodology. How does the viewer know what's right and wrong in the literature these days with so much out there?
Yeah, that's a great question. So, and that was the point of sort of updating the 2000. Really, there's the data. So in 2000, we only had a limited amount of data, so we fitted a straight line through it. But now looking at many more data points, it is stress dependent. And same with the geosynthetic interfaces. So in general, whatever material you're modeling, whether it's the waste, the geosynthetics, the low strength waste, you should start or assume that it's a stress dependent envelope and then go from there. If you can prove it's a linear envelope, then you can change back, but always start with a stress dependent envelope because you over predict the strength at higher normal stresses. Just take this graph right here. This is our 2000 recommendation, Eat et al. 2000. There's the straight line. Look at the difference at a normal stress of like a 1200 kPa. That's how much we over predicted the strength because we didn't use a stress dependent envelope. That vertical distance from the straight line to these two lines.
All right, I think that that was our last question. So before we end, I want to encourage everyone to visit the FGI and the IGS North American websites shown on our last screen in today's presentation, and to consider joining. We can't put on these webinars without you. Membership in these geosynthetic industry groups is important. Thanks again, Tim. And thank you everyone for attending. We appreciate your interest in attending today's webinar. If you have questions, please feel free to reach out to us. And with that, we will conclude.
Thanks, John.